So we this is a vibration test one correction. So we're given problem one, which is for test one, to find the spring equivalent constant of the system shown in the following figure. We have the figure right here, and then these are in series and these are parallel to each other. So K1, since they're in series, we decide to go with K plus K equals K2, and then K equivalence of this section right here is going to be this divided by 2 because they're in parallel. So we do exactly that for K3, which is the after result of this, guys, showing us like a little example over here. K1, KQ after this, and KQ2, and KQ3. So after doing that, we had to sum up of K1 and K2 equals K4, which we have the equation over here. Solving for that equals um, 2K plus K over 2, which are already solved over there, giving us 5K over 2. Then we move on with KQ4, which is the final conclusion of the right side. And then since they're in series over here, we do exactly the same thing for KQ3, which is K plus K over 2K, and then the force outside, and then we calculate for KEQ5 consisting of K4 and K equivalent 4, the equivalent constant for 3 and equivalent constant. We solve the equation, giving us 10 over 9K as K as spring constant, equivalent constant, sorry. And then moving on to test 2. So test 1, problem 2. We're given a figure and we're told we're given all the dimensions, the diameter with 1 microcoulombs of the plate, the beam of the length of the beam acting on the plate, and then we have the length of the width of the plate and the height of the plate. We have the thickness. We have the density of the material. Excuse me. Then we are told to calculate the equivalent mass of the system when the dynamic system is evaluated at the center of the plate. This is the center of the plate, and then we are told to calculate the dynamic, the mass equivalent of this entire system. So the equation for this is the mass equivalent equals the MP plus the mass equivalent outside of the height. Then we are this is our equation, simplifying what MP and MH is equals to this solved out equation. Then we come back again to the main equation and plug in all the known values we solved out here, and giving us the final answer equals 4.743 times 10 to the power negative 3 in kilograms. So problem 3, we're given this whole entire figure, and we're told to determine the equivalent torsional stiffness of shaft 2, which is this shaft over here, which is shaded. And this whole figure out consists of the shaft, which is the beam right here acting on D2, and then we have the bearings, which are the shaded ones, and then we have the gears, which are this basically the lines acting on there. So we're given G equals 10 gigapascal, but we converted that into mass meters per pascal. So we did D1 with dimensions given. As I said, meters pascal is megapascal. Sorry. We given D1 and D2, D3, which are all stated on in the figure. The same for each dimension is all given. Then I decided to go with a more interesting figure that gives me a better understanding, basically converting this whole equation, this whole figure into a spring setup. So I knowing the K equivalence of 1 this session and K equivalence of 3 this session, and then knowing what's happening here, which is N1 and N2 for K equivalent 1, and N4 and N3 K equivalent 3. Then making this solve for the total spring equivalent constant, at K1 and K2 and K3, and then solving for what each part is, which is N2 and N1, which are given right here. We have all this set up, and we actually calculated the K equivalence, plugging in the equation, plugging in our givens into the equation, then we get 11.57 kilonewtons per meter. Moving on to test problem 4. We're given an interesting figure where we have a spring, we have a roller, and then roller moves up to the x direction towards the our left side. Then we have K1 on the right side and K2 at the left side. So this is the formula for K1 and K2. And then we are told for number 1 of problem 4 to determine the degree of freedom, which you have x on this direction, and then the angle of where it's moving at. So we have the constraints, and then we have 2 minus 1, which is 1, which is a degree of freedom. Now we're told to find the total potential energy associated with the system. This is pretty straightforward. It's more finding out potential energy, which is U1 at K1 and U2 on the other side. They have the same movement, the same equation. So we just basically simplify into a more simple equation, just like our K1 is known up here and K2 is known up here. We just plug them for the equation over here. So moving on to question 3 of problem 4 in test 1, we're told to find the total kinematic energy associated with the system. Exactly the same way we saw for number 3 with the potential energy. We did the same thing for the total. That's a translation and rotation, so of the roller. So we did the same thing, which is 1/2 the mass, and then the roller times the x dot square plus the same thing, but using the translation and the rotational. So from problem 4, we're taught to formulate the dynamic equation for the system, which is this mass equivalent x double dot plus the spring equivalent constant kq, x equals 0. So where we have potential and kinematic energy equation, we already solved for them, so we basically use them and plug them in for the KEQ and MEQ, and we get this equation. Get our final answers over here. Then for number 5, we are told to determine the system natural frequency, which is a general equation as omega n equals the square root of the K equivalent, the spring constant and the mass equivalent. Well, using the solved equation above the number 4, we plug it into this equation. This is what we get for our natural frequency. And moving on to problem 5, we have of test 1, we have this whole figure. Then I decided to move on. I decided to create a free body diagram with the force and the mass of the whole system. Then our question was to find the equation of motion, which was F equals the mass times the x double dot. So our forces are all acting on K1 and K2, and this damping rate system, damping ratio on there. So these are the forces acting on the mass, and so we have this, and then spring constants on the spring side, and then the damping C, which equals to the mass x double dot. So where omega n is a typical general equation in scale of m, we have this equation right here where the 2 times the damping ratio times omega n equals Cm. Then we plug that in for this equation over here, and that's how we get the equation of motion. And then for number 2, we're told to calculate the undamped natural frequency, omega n, and the damping ratio, which is the symbol. So we did the same thing, omega n, the known general equation, 1/1 equals 1 radians per second. And then damping equation, damping ratio, we did the C over M over here, but like simplify what the damping ratio is. Basically simplify this whole formula right here, and we plug in all our knowns and we get 0.6, which is less than 1, and then we assume that that is undamped. Then moving on to what is the general response equation, and we are told to, like, we can keep unknowns in the expression. So we did exactly this, found this equation in the textbook, where omega n, omega d equals to the square root of 1, and then we have the damping ratio of 2, times omega n. And pretty much most of them I don't really know much of what they are, but this is exactly what I found in the textbook. So for the general response, for number 4, pretty much the last question of test 1, problem 5, we are told to told that if the block is put down at 0.15 meters and released from the rest, we should find the response at xt, which is the general response. So we said that since it's put it down, x of 0 is equals to 0.15, which is given to us. Then the derivative of that is 0. So using our general response equation, we solve for x out of the general equation, and then we get this one, this equation right here with excuse me, which gives us the 0.1875 with known and given values using the above equations on number 2. And we actually solve for rho, which is our tan inverse of the whole equation above us, being simplified, and then we get 0.927 rads, and then we plug back all our knowns back into the general equation, giving us our final answer for number 4. And this is test 1, problem 5 concluded. Test 4, test 1, problem 4 concluded. Test 3, test 1, problem 3 concluded. Test 1, problem 2 concluded, and test 1 concluded. Thank you.